Okay, welcome to Controversy. This PowerPoint is aimed at getting to understand a little bit about nuclear power, nuclear energy, its uses, risks, and obviously the controversy surrounding it, surrounding the use of nuclear energy as a power source. As you can see, we have a PowerPoint to run through that will take you through the ins and outs and the sort of do's and don'ts of nuclear energy. All right, so the question here is, should Australia employ the use of nuclear power for energy production? And that's what we're going to explore here. All right, so basically you need to make the distinction between what is a non-renewable energy source and what is a renewable energy source. You may already know this, but just to make sure, a non-renewable energy source is an energy source that can run out, that can be used up completely. And the standard one, the typical one that we think of when we look at energy sources that will eventually run out are fossil fuels. We call them fossil fuels because they basically organic material, so material that comes from something being alive, being sort of sequestered into the ground over time. So in other words, being laid down over layers deep under the earth over millions and millions of years, basically making a really concentrated form of carbon, okay? And because it takes so long to make fossil fuels, and we call it fossil fuels because they do come from sort of the dinosaur time and before that as well, hundreds of millions of years of time. It's mostly vegetation, forests that have existed a long, long time ago and have ended up laid in the earth. When you look at coal, oil, and natural gas, they are all cousins of each other. Oil is the most energy rich. It's the best version of fossil fuel that you can get. It gives you the most energy. Coal is next, and then gas is third, basically. Gas often comes up as natural gas comes up as a byproduct from mining, and is really, really useful, but not particularly high energy. So when we say non-renewable, because we are looking at material that takes such a long time to be created, that we use it much more quickly than it can be created. So eventually, it is possible to have dug it all up or drained it all out and used it all up, meaning that there's none left. Okay, and so for an economy and a world and sort of a modern world that is incredibly energy hungry, if you're making electricity out of burning coal and burning oil and things like gas, then eventually you're going to need to come up with an alternative, because when that stuff runs out, then you've got nothing else to power your huge machines of industry. Okay, all right, so if we go through and say, okay, why do we call them fossil fuels? I've already hinted at that. This slide goes through the basics of why we call them fossil fuels. They're fossil fuels simply because they're very old. They've been buried in the earth for a really, really long time. As plants and vegetation live and die and go through their life cycle and become layered over, moving earth, basically what happens is, given enough time, most of that matter breaks down and compresses down, and there's a whole bunch of chemistry or chemical changes that happen that eventually lead to large coal and oil reserves. Now, there are places on the earth where you'll have noticed that we do have oil rigs and oil refineries out in the ocean, and that's because the oceans and the earth does move a lot over time. It doesn't look like it moves around very quickly. I mean, on the human lifetime and human scale, the maps of the world pretty much stay the same all of the time. But if you could go back 1,000,000 years, 10 million years, 100 million years, the Earth would not look anything like it does today. And it's because the crust of the Earth, which includes all of the dry land, all of the oceans, that the outer layers of the Earth move around all of the time, and they move very, very slowly. But we know that movement happens because of the evidence provided by things like earthquakes, volcanoes, and things like that. So yes, we get oil out in the middle of the ocean because that part of the land wasn't the middle of the ocean once. Okay, and hence why I chucked a little image of an oil rig out there in the ocean, okay, pumping out oil. We don't usually go for coal under the ocean. We pretty much stick to oil because it's the easiest to get in that situation, and it's also the sort of the richest prize. It's the most energy you can get out of it. So powering all of our cars and industry for a really, really long time. That's not dawdle. Okay, there is a problem that has sprung up sort of as the internet has grown, and everyone gets a voice basically, okay? So you will hear a lot of, this all leads into climate science and climate change, okay? Now, there are a lot of people out there who try to deny lots of things that we know are fact, okay? That some of the things that we know that are fact are that the temperature of the Earth is changing. It's even changed between the 70s and now, let alone from the beginning of the Industrial Revolution when we started to really pollute the atmosphere. Okay, so there are people who will deny that there is any truth to climate change. They'll call it a theory, okay? And in addition to that, you'll find some people even will say things like, oh, fossil fuels they're not the product of ancient forests that have decayed and been compacted over millions of years. No, that coal is naturally occurring. You'll find it anyway. It's never going to run out. Okay. Now, these people are the groups that try to encourage that kind of thought and that kind of debate over things that just aren't real. We liken them to this very old sort of saying that we have. Where this is a great cartoon to really describe where the sort of the climate change, the deniers, and really sit. Okay, so this here is a picture of a frog inside a pot on a stove. The saying goes, if you throw a frog into hot water, it will jump out straight away because it knows it's bad. It's obviously not comfortable, not good. But if you put a frog in cold water and slowly turn up the heat, it gets used to the heat. And the idea is that eventually it'll probably just die in there without realizing that there's a problem. And that is the idea. That is the analogy that we use for people who are creating huge lobby groups and arguments and discussions over, oh, well, climate change isn't real. Parts of the world are really cold and other parts of the world are really hot, and that's always been the way. And they like to ignore a lot of the scientific evidence, okay? Now, there's a really important reason for that, okay? And the reason for that is because most of your climate science deniers and alternative theorists are usually funded quite heavily by big oil, okay? So there's a lot of people out there who make a huge amount of money out of the existing status quo of mining coal, pumping oil, selling tons of petrol. There are countries in the Middle East where nobody has to pay tax because all of the money that they earn for that country comes from the sale of oil, okay? So oil has basically made itself incredibly important in our society. So now, because it's really important and there's a whole lot of structure put in place around it to protect it, you end up with a lot of people who are very frightened of talk like alternative energies and let's try and stop using coal and oil because the atmosphere of the Earth is changing dramatically faster and faster. So you'll have a lot of people who go in to try and confuse and create it creates speculation and mistrust on what is really clear science, okay? And just to put a face to it, I thought I'd show you these two fellows. Now, you can see this is Koch Industries. It's an unfortunate name, I get it, but K-O-C-H is pronounced Koch. These are the Koch brothers. They, we think that their estimated combined value, these brothers, is about $100 billion. It is the most stereotypical oil family that you can get. Okay, they own the second biggest company in the United States, second biggest private company in the United States. All right, they have been linked to funding hundreds and hundreds of organizations out there that are made up of actually very small numbers of people individually that are constantly attacking climate science, attacking the evidence, attacking the scientists, attacking the reality of what's going on. Because, I mean, obviously, their wealth and their power is tied incredibly strongly to their oil business, okay? And so this is what I'm getting at. I want you to understand that when it comes to climate change and what fossil fuels are and what they do, what their effects are, there is no actual debate, okay? There is no, oh, well, that's just a theory. Climate change is as much a theory as evolution is, okay? It is what is going on, all right? So don't ever let yourself get sucked into any kind of argument there. So, fossil fuels are made from ancient forests that locked away vast amounts of carbon many, many millions of years ago. Climate change is not a theory, it is a fact. And if we switched fully, this is a scary one, if we switched fully to renewable energy today, it is still technically too late. We need to actually not only switch to alternative fuels that don't impact on the atmosphere as quickly as possible, but we also need to put in a whole lot of strategies designed to strip the carbon dioxide that we've already put in the atmosphere out again. And that science exists. That is actually not as hard as it sounds. All it really takes is people to want to do it and find the value in doing it. Okay, so now let's move to renewable energies. Renewable energy sources, things like wind, solar, geothermal, hydro. So solar, don't need to explain, pretty obvious. We have things like solar farms, and we also have a lot of solar panels out there. This is actually a really good way of harnessing energy and at the very least, offsetting the reliance on things like fossil fuels. Wind, again, obvious. And hydro is where people will often find a river somewhere that is always flowing, okay? And what we can do is dam it. So you build a dam across that river. It floods a valley, okay, which is obviously not that great for the valley. And once the valley's flooded, it gives you a huge amount of stored potential energy in that water being elevated above the ground. So what we do with that is we allow the water to fall through very long pipes that as the water falls from the top of the dam down to the bottom of the dam, we run it past turbines. The turbines spin generators, and the generators make electricity. And as long as it keeps raining in whatever region this dam is in, you will never run out of electricity. There are some huge places. Australia has the Snowy Mountain hydro scheme, so we use it in Australia. I know that the United States uses it a lot, and China in the last few years built some of the biggest hydroelectric dams and projects in the world because they've got some enormous Great Lakes out there that they use for it. Okay, so this is the idea of a renewable energy source. So where does a nuclear energy fit into this? Glad you asked. Well, nuclear energy is not technically renewable. When you do a little bit of science, you find out that uranium, which is what a lot of the nuclear energy is based on, is a radioactive material that you dig up out of the earth. So it does go back to a bit of mining. Now, the process of digging up and processing uranium to a point where you can actually use it to make energy, that process itself is actually quite dirty and really quite dangerous. It has to be managed and looked after really well. Okay, so once you dig up all of the uranium, then you won't have any more. So it is not technically renewable. However, the world and Australia has a staggering amount of uranium buried in the earth. And uranium is such high value, and it's such a high value energy source that it is very hard to believe that uranium would ever run out for our uses. Not only can you dig it out, purify it, use it to make energy for huge amounts of time, but the waste products in modern reactors and modern power producing systems is taken and re-enriched often to a point where it can continue to be used. And so from a small amount of uranium, you find that you have a huge amount of energy for quite a long time. And because there is so much uranium in the earth, then it is often referred to as another renewable energy source. It's kind of thrown in the same camp simply because it's kind of impossible almost to run out of it. Okay, so that's why we have linked nuclear energy in with the with climate change and with the whole renewable energy debate. Okay, now an interesting thing when it comes to Australia particularly is that Australia actually has 30%. It is predicted that Australia has 30% of the world's reserves of uranium buried in the earth. So Australia is an incredibly old continent. If you want to find the oldest rocks on the planet, you need to go to Western Australia. There are no rocks anywhere else in the world that you can find that are quite as old as the ones that you can find in Western Australia. They are almost as old as the Earth itself. Okay, meaning that Australia is a continent that has had very little change happen to it over the billions of years that this planet's been here. And part of the byproduct of that is that whatever was here when it formed is still here now. And so when the planet formed, and uranium was one of the many elements that are created in the process of planet formation and star life cycle, a lot of that uranium ended up here. And uranium, as valuable as oil is, uranium itself is far more valuable. Okay, so economically, you'd see that Australia stands to gain a lot from mining uranium, and not only using it ourselves, but selling it to everybody else. So there is a very strong economic argument for doing it. And you might be wondering, well, why don't we do it? And what's the big deal? Why does Australia continue to burn a lot of coal power stations and a lot of oil and gas? Why, when we have so much uranium in our country, that we still persist with what we know is causing a huge environmental problem? Okay, and that's what we're sort of talking about here. Okay, now the reason uranium is sometimes referred to as a really good alternative to burning fossil fuels is because the production of energy using uranium does not produce any greenhouse gases. Okay, the whole process is contained, it's self-contained. The core of a nuclear reactor gets super hot when you get the right amount of nuclear material together. And when it gets really hot, what we do is we run pipes through it, and those pipes are full of water. That water boils, and once it boils, it becomes steam, high pressure steam, and the steam turns turbines, and the turbines make electricity, the steam cools down, becomes water again, and goes back through the cycle again. Nothing actually comes out of a nuclear reactor other than energy, okay, during its normal operation. And when you look at this slide here, you can see how much energy it's worth. Now, I've included an image here of a man's hand holding what is basically a uranium pellet. These little black pellets, about that big, thousands of them are used to fill the rods inside a nuclear reactor. Now, here we have a graphic that tells you how much energy these little pellets are worth. So when you look at one little uranium pellet, it's worth about 3 42-gallon barrels of oil. That's the same amount of energy that you get out of one pellet, or 1,000 kilos of coal. Okay, so a ton of coal. And because this is an American graphic, and I know they still hang on to using feet and inches, all that nonsense, but 17,000 cubic feet of natural gas, and so if you don't know what a foot is, basically about that big. All right, so 17,000 cubic feet of natural gas is what one of these little pellets is actually worth. All right, so you can see there that energy, you do get a huge amount of energy out of it, and some countries do use nuclear power plants a lot. So the United States uses it a lot. I know Japan definitely uses it, and so do the French. There's a lot of European countries that use nuclear power, and the Russians definitely. Okay, so when you're looking at the value of the material that you're using, and the fact that when you do use it, you don't pump out any greenhouse gases. Okay, so you can, by using these energy sources, you can end up stabilizing the atmosphere and stop climate change or help reverse it. Okay, just one more word on the value that you get out of nuclear power. This here is an image of a nuclear powered submarine. This is an American submarine, and it is powered by a small reactor. So they build a mini version of what they use to power cities, and they build a mini version of it, and usually there's a pair of cores inside something like a submarine or an aircraft carrier. So the Americans, the Russians, and a few others use nuclear power to power their, basically, weapons of war. And just to give you an idea of how much energy is stored in that core, until recently, when they build these super technical, very advanced submarines, and they put a core in them, a nuclear core in them, that nuclear core will last about 25 years. So it's almost the length of the life of the submarine itself. So it's basically filling up the sub with fuel and never having to fill it up again for the whole life, for its whole operational life. Like, that is how much energy is packed in your nuclear material. The way we produce energy has to change, okay? Because the way we're doing it now unlocks carbon from millions of years ago and continually adds it to the environment that we already have. And the environment that we already have came along nice and stable, and that's where we evolved and how we've ended up here. All right? Now, when we start changing the environment, then we're changing it away from what actually suits us right now. Okay? So, the carbon cycle is a nice closed loop of carbon dioxide moving through the air into the plants, into the animals, and then back into the air again. Okay? So the amount of carbon dioxide in the environment tends to be pretty stable. Then we come along and we dig up oil, coal, gas, and burn it all. So we've taken the carbon dioxide that was already there, which was good, okay, and started adding lots and lots more of it. Okay? Now, why is that a problem? Another excellent question. It's a problem because of something called the greenhouse effect. The greenhouse effect is actually a good thing. You need a greenhouse effect. Without a greenhouse effect, the temperature difference on the ground between standing in the shade and standing in the sun is incredibly big. So for example, go for a little walk on the moon without your proper protective spacesuit, and the temperature on the moon, because the moon has no atmosphere at all, there is nothing to stabilize the temperature. When you're standing in the sun, you can hit a maximum of about 127 degrees Celsius. Okay, that's way past boiling. Stand in the shade, and in the shade you can vary from negative 53 degrees, negative 173 degrees. So what you're looking at there is the absence of an atmosphere, the absence of a complete greenhouse effect means the place is pretty darn hostile. Can't really live there, can't really do anything there. But you can go to the other side of that scale as well. The other side of the scale is our friend Venus, our true sister planet. Everyone bangs on about Mars, which is only about a third the size of Earth and has a very thin atmosphere. But in reality, Venus is actually in the right part of space, in the right orbit around the sun, that it could be like Earth. Venus is almost the same size as Earth, so living on Venus would be pretty good. It seems a lot more logical a planet to spend time on than Mars is. But the problem is, Venus went through a few little problems in its formation. And what you look at when you see images of Venus is what you're looking at is a thick cloud cover. Now, the thick cloud cover of Venus is so thick, in fact, that it has what's known as a runaway greenhouse effect. Okay, so now think about it. This is a planet that is the same size as Earth and it's in the same region of space around its star, just like Earth, and it has a runaway greenhouse effect. Mercury, the metal mercury on Earth is in liquid form. On Venus, lead is in liquid form. That's how hot the atmosphere is and how much there's a staggering amount of pressure down there as well. So you can't land on it, you can't walk around on it. It is burning hot and it is really, really, really high pressure. So it is a completely dead world because its greenhouse effect is just completely the other way, okay? So we know of what a greenhouse effect is and how it acts and how it works, okay? On Earth, we have a nice happy medium. We have some carbon dioxide in our atmosphere. It traps some of the energy of the sun, not all of it, okay, like Venus does. And it means it keeps a nice warm blanket around us, okay? So that when you go in the temperature differences on Earth, you know, sort of highly populated areas and places with lots of biodiversity, the temperature ranges are actually a lot smaller, day to day than they are on these other hostile worlds. And so the greenhouse effect is a good thing. The problem that we have is that when we add carbon dioxide and other greenhouse gases to the atmosphere, our temperature starts to go up. And if the temperature goes up, then our climate changes. And the climate isn't just hot days and cold days. The climate is tornadoes. The climate is sea level rising. The ice caps melting. There are areas. This is an image of, the McCarty Glacier in Alaska in 1909. This glacier was permanent. It was always there. There was never a time when that big chunk of ice wasn't there. Here we have, in 2004, the glacier is completely gone, and most of the ice that was clinging to these rocks up here, these little mountains, is gone as well. There are some pretty massive hints that the planet is warming slowly. One more example of that is something called Tornado Alley. There's a line across the United States that you can draw, and along that line there's basically a corridor going across it that is called Tornado Alley. So every year when that particular season hits, you get a huge concentration of tornadoes ripping across the United States along that line. Something we've noticed over the past few decades is that Tornado Alley is getting wider. All right, so it's getting much wider. The people are getting devastating tornadoes in areas where they've never had them before. Again, the evidence for these big shifts and changes is pretty strong. So, why is nuclear energy, with all its benefits, why is it controversial? What could go wrong? I mean, at your age right now, watching this, you've possibly heard a few of the big sort of accidents that have happened in the past around nuclear energy. See, the issue with nuclear energy is that nuclear energy comes about from something called radiation. And although radiation is a very common thing and comes from the Earth itself, comes from space through the clouds, it comes from your microwave, it comes from the lights. I mean, when you're talking about radiation, we have lots and lots of different kinds of radiation, and only some of them are actually harmful. I mean, even your radio signals that your television arrives at home with is a form of radiation. But we have something called ionizing radiation. Ionizing radiation is kind of dangerous to living things. And we have three kinds of ionizing radiation, and guess where they come from? They come from nuclear reactions. So, when you build a nuclear power plant, a huge amount of effort goes into containing that nuclear power plant, because if you were to let that material out, it would cause widespread devastation. Okay, so you would end up with basically what is known as radiation sickness. Basically, breaks apart your DNA. When we look at where nuclear energy comes from, something that you're going to study basically next term in Year 7 is the periodic table, all right, and the periodic table of elements, and part of that will be the image, a very common image of what an atom looks like. So an atom has a nucleus, which is the middle, and it's got electrons that whiz around the outside. So in what we call shells, all right? So nuclear energy comes from the nucleus of an atom. So if you get yourself some atoms that have lots and lots of parts in the middle, those atoms, I like to call them nice big juicy atoms, what happens is they struggle to hold themselves together. And once they get past a certain size, the forces that we have in nature that hold them together sometimes fail and allow some random nucleus to break into two separate bunches. And when it does that, it releases energy, okay? So it releases energy and particles, okay? Those particles are high energy, and those particles are really, like I said, dangerous to human life, all right, or any kind of life, really. So nuclear energy, that's where nuclear energy comes from, all right? When we look at the periodic table of elements, this is a list of all of the things that exist in the universe, all of the materials that are around you, make up your body, and everything that you can touch, smell, or taste, or feel, is made up of some combination of these materials that we have found, okay? The ones that are down here, let's see, down here, so 89, there's uranium right here, okay? So all of these heavy elements tend to be really radioactive. They tend to be very unstable, okay? So what happens is they naturally give off energy. So what we do is we dig them up, concentrate them, make them really clean, and then we make sure that they give us lots of energy, all right? And that's how it works. And in an ideal world, nothing goes wrong. This system works really, really well, okay? So here's a graphic of the different kinds of radiation that come out from nuclear reactions and their penetrating effect. So this version of radiation doesn't really even get through the air, let alone through a t-shirt. It's a very weak form of radiation called alpha particle radiation. Beta particle is a little bit more high energy and can penetrate your t-shirt and your body quite easily. And gamma rays, which is kind of what we use to do x-rays, Gamma rays are incredibly penetrating and pass right through you, okay? So you can see that this kind of radiation does have a really strong penetrating effect. What we do to make energy though is when we contain it properly and we allow a process of fission to occur, we take these big juicy atoms like uranium and plutonium and stuff, and like really nice, like big radioactive atoms like that, and we wait for them to decay. And when they decay, they basically break into separate bunches. And in that breaking process, parts of them go flying out and lots of energy is released, okay? And that energy is what we use to boil water, make steam, turn turbines, make electricity, and, you know, have Wi-Fi and light and really good things like that. Here I have a really cool demonstration. If I have a big, like a kilo of this material, okay? Every atom in there has sort of like a 50-50 chance of splitting or not splitting at any one time. We can do all sorts of calculations using that time because different radioactive materials will split at different rates. And so we can do all sorts of funky things like figure out how old rocks are, how old a planet is. This is why we know how old a planet is. This kind of science for a really long time. And if you looked at my evolution video earlier, you will have seen that, you know, there were some huge, incredibly wrong guesses at how old the Earth was. We only really found out when we understood radiation, okay? And like I said, that's kind of how we know because there's a lot of rocks in Western Australia that are incredibly old, okay? And we use radioactivity to make those estimates, okay? This here is a Geiger counter, all right? Every time you hear it click, can you hear it? Every time you hear it click, one of these particles has hit the sensor, okay? So you can see that radiation occurs in nature. So you hear a little click. Oh, there's another one. All right. Now there are some materials that contain way more radiation than others. Okay, so here I'm wearing gloves to be a little bit safer because nobody needs this stuff in their bodies. This is a piece of rock that a person that used to work at this school found out in the bush and recognised it for what it was. So if I bring this rock, now this rock was found years and years ago and it's been sitting in the desert for millions of years. You can see that this rock is radioactive. And this is just lying out in the bush, okay? So radiation is something that is naturally occurring, okay? Nothing to be particularly alarmed about. But when you dig a little bit and you take another sample, you find that the atoms inside some samples are actually far more energetic. And so what we have here is another sample. This is a sample that is designed and made for schools to demonstrate things like what I'm doing right now, okay? So here, this is I think this is an alpha emitter. So probably the weakest kind of radiation, all right? And if I bring this you can see that there is a huge number of particles pouring out of this, okay? Now these are alpha particles, so even the thickness of the atmosphere is enough to shield you from it, okay? Which is why I'm not particularly worried, and I do this little demo every year. Hold it up here, and you get almost no real difference. So in other words, the air gap between the sensor and this sample is enough to stop almost every particle from actually getting to the center, okay? Bring it close, and the particles are actually getting through the atmosphere. Now, the kind of trippiest thing about this is that when you read the label, first you see this label is typed, okay? No one does that anymore. And we'll see, okay, so this is a sample of radium, okay, so it's on the periodic table. Radium discovered by Marie and Pierre Curie, Okay, and it was encased inside this metal container. So it's only a tiny piece inside. This thing is mostly a container. And it was packaged in 1974. Okay, I was 2 years old when this sample was created, put in this container, and sold to a school. All right, 1974. Okay, so it has been doing this 24 hours a day, 7 days a week, every day of the year since 1974, and it's still going crazy. This tells you, I hope this does is it shows you that radioactive materials, when they're potent, when they're quite strong, they can be quite dangerous. So, what do we do with nuclear waste once it becomes waste? This is a modern version of what we do. We find a place out in the desert, somewhere far away from people, and we encase it in concrete and lead barrels. And then we just put it down in these nice long rows that may eventually be buried or just supervised for the rest of human existence, basically. That's how dangerous it is. In the old days, some governments tried encasing them in barrels and throwing them into the bottom of the ocean. But of course, a lot of environmentalists turned up and said, you can't really do that because what if they leak and then you end up with a bunch of radiation in the ocean? I mean, in reality, you probably wouldn't notice that the ocean is pretty damn big, but still not a great thing. The idea really is containment. Over here, they're going to bury them. So all these yellow barrels are full of nuclear waste. We make a lot of nuclear waste every year, and the more nuclear energy you use, the more waste you're going to have. And that waste has what is known as a half-life that is incredibly long, which means that you're looking at something on the scale of billions of years being dangerous for billions of years rather than just a few thousand years or something like that, okay? So the problem with those pellets once they're used up is, what do you do with them? There's a lot of waste out there. Australia has a lot of empty space in it, and so again the debate rages over us whether we should be using our nuclear energy or not, using our reserves. So you can see here, these yellow circles here have been proposed as nuclear reactor sites. They were proposed. They didn't actually happen. In green, we're looking at possible nuclear power station sites identified by a think tank in Australia. So again, the idea of using nuclear energy and then also storing the waste has been around for quite a long time, and we still, as the climate continues to change, the planet warms, the debate around whether we should be using nuclear energy or not continues to get stronger and stronger, okay? Which is why we have this whole section in our controversy unit. Can things go wrong? Well, yes, they can, and they have. Back in 1986, in the former Soviet Republic, in the country of Ukraine, they had several nuclear power plants, and they lost control of one of them. Okay, so the reactor melted down, and when it melted down, it blew the roof off the reactor core, and it just spewed tons of nuclear smoke and debris out into the atmosphere. All of the first responders that went to fight the fire, pretty much they all died over the next month, horribly, because they did not realize that that's what actually happened. They didn't realize that what the fire they were fighting was actually from the core. This happened in 1986. This is a town. This is not the reactor, but this is a town. So there was the reactor, which employed a lot of people to run it, and those people tended to live in this town here, which is really close to the reactor at Chernobyl. This is, I think, called Pripyat. Anyway, it was so close that when the reactor exploded, they lined up hundreds of buses and grabbed everybody living in these apartments, and they all basically took them away in one night because they realized how dangerous the situation had become. This area is still radioactive today. The reactor at Chernobyl, which is a little bit away from here, is very radioactive and is still out of bounds. You can visit, you can see there are actually some people here in this photo. You can visit this ghost town, but you're not allowed to stay there for very long because that you end up absorbing way too much radiation over a long period of time. And so you can kind of do a touristy thing there just to see the freakish sight of a completely empty town. But yeah, you can't live there, definitely not. And the reactor itself will be radioactive and dangerous until the end of the Earth, basically. See, that's kind of the scale that you're looking at when you're talking about nuclear accidents. The half-life of nuclear material on that scale is so long that even our sun won't last long enough for it to become safe again. So they're the kinds of stakes that you're playing at, okay, when it comes to accidents of these sorts. Will it ever happen again? Of course not. We've learnt our lesson. Humans are smart. We're going to figure out a better way of doing this. Since when are we ever going to let that happen again? Oops. 2011, we had a tsunami. Tsunami went through, hit the coast of Japan. And basically, after a whole lot of failures, caused several of the reactor cores at the Fukushima site to explode. And again, Japan copped its Chernobyl, alright? So, lost containment of their cores, they exploded, that whole region is now toxic. A whole lot of people in the surrounding farmland have gone, well, what am I going to do? Where am I going to go? I can't sell my land. I'm going to have no money if I leave. And, there's a whole bunch of old Japanese people who just continue to live around the site because they refuse to leave and run the risk of basically getting cancer and all sorts of other problems associated with radioactive exposure. Like mild radiation leads to mutations. And so there's apparently the Fukushima's mutant butterfly. So the butterflies flying around, moving around, being exposed to the radiation. They tend to have smaller wings, they have damaged eyes, they are not forming properly. So there's lots and lots of little things that happen as a result of prolonged radioactive exposure. And here's a graphic that if you're looking through the PowerPoint, in association with watching this video, you can see by reading through here all of the huge amounts of problems that radiation can cause to a human body. Okay, so all sorts of things like leukemia, so all the blood diseases, things like that can be brought in. Actually, in Chernobyl, there's the hospital where in that town, in that ghost town that I showed you in that graphic earlier, there's a hospital in there, and if you go to that hospital, you can see in the bottom of the at the bottom of the elevator shaft, there's a huge pile of clothes that are just sitting there today even, and they're all horribly radioactive. Basically, all the people who were fighting the fire at Chernobyl were brought into this hospital, and the nurses eventually and the doctors realized that these guys coming in were heavily radioactive. It was covered, radioactive material covering their clothes all through their bodies. They were dying, and it was really, really, really horrible. So they stripped all those contaminated clothes off them in their attempts to help them, and because they knew that they were dangerous, they threw them down an open elevator shaft, and they all just piled up in the floor down in the basement. Eventually, all those guys died, and those clothes are still sitting there. There are fields full of trucks and jeeps and all sorts, and helicopters that just lined up in a field and fenced off because they are covered in radioactive material from the accident. Even today, they're all just still sitting there rusting away because they're too dangerous to use and too expensive to try and clean. So yeah, when things go bad with nuclear power, they go really, really bad, okay? And this is kind of where the controversy comes in, okay? So when we're asking you as students to look into an issue of controversy, this is where your critical thinking comes in. And in your critical thinking, you've got to say to yourself, asking yourself questions like, okay, pros and cons are, do the benefits outweigh the risks? There are currently about 450 nuclear power reactors operating in the world today, okay? If we were to replace all of our coal and oil and gas, that number would be huge, all right? Much, much bigger than that, and obviously the issue of waste would then become even more significant, all right? Both the United States and Russia operate large fleets that use nuclear power reactors, okay? We've been operating nuclear power plants since the 1950s. That's when the science first became viable, okay? So we've had it going for about 70 years, okay? In that time, we've only had two major incidents, Fukushima and Chernobyl, okay? And out of both of those accidents, huge changes were made to all other reactors to make sure that such things couldn't happen again. Well, those specific things can't happen again. So, do the risks outweigh the benefits? That's the question that you really need to ask yourself, okay? That is the conclusion of this video. Hope you enjoyed it and found some interesting ideas in there, okay? So, thanks for watching.